Okay, say I'm working with a binary decision diagram library in Python. I build a BDD for some formula, and I want to understand its shape. I'm in the REPL, so I do the standard thing. I print it, and I get this. Now, anybody who's worked with sort of any interesting data structure, matrices, trees, BDDs, knows this isn't super useful. To make any sense of it, I have to grab a pen and paper, squint at all those nested constructors, and start drawing. What would really help me if I could see something like this. The same Python value drawn the way we think of BDDs. Nodes layered and grouped by variables, distinct high and low edges, shared terminals. I mean, they're called binary decision diagrams after all, right? So why can't I do this every time I want to inspect a value? Because the usual way we get a picture is writing drawing code. Before the picture can tell you anything, you have to choose marks, compute positions, handle updates, basically manage a pile of rendering mechanics. A tiny amount of anything you write will actually capture BDD conventions. Most of it is just scaffolding. This talk is about Spatial, a language designed to tackle this problem. The goal of this work is for diagrams to be as cheap as printing. Every time you inspect a value, at the REPL, in a debugger, printf, whatever, you should have the option of seeing a diagram. And I don't think I have to convince anyone here this is obviously a PL problem, right? Expressing diagramming in terms of a language, and you can get a lot of important properties by design, right? The diagram is guaranteed faithful to the value being inspected. You wouldn't want your REPL output to lie to you. And when a diagram cannot be generated, the failure is semantic and can be explained in terms of your value. Let's go back to the BDD REPL output. The first thing I want you to see is that there's already a diagram here. All the atoms in the REPL output, basically constructor terms, ints, and strings, are nodes, and the fields, node ID, high and low, are edges. And once we add some quality of life improvements like deduplicating things and coloring by types by color, you get something like this. This is what Spatial reconstructs for you for free. No drawing code, no annotations, nothing. Every box is an atom of the value. Every arrow is a field. The problem is, this isn't the picture you want to see for a BDD, right? But with a little refinement, it can be. First, hide implementation details you don't care about, like node IDs and the none type. Then, arrange nodes so that parents sit above children. Horizontally align nodes that test the same variable and group by those variables. All right. And if you want a little visual zhuzh, distinguish nodes and edges by color and styling, and that's the diagram from the start of the talk. We didn't write any rendering code. We just specified how it should be arranged. So that's the workflow end to end. Start with a faithful graph, write some rules to refine it. When it's good enough for your purposes, stop. Basically, you want something that's useful, not necessarily pretty. I call this diagramming by refinement. To paraphrase Michelangelo, David was already in the marble, the BDD is already in the diagram graph. It's all there. And the nice thing is, it's not just a picture. This is kind of this way. Yeah, in this video, dragging things around is generally useful when you're exploring a value. In this video, I'm trying to basically move nodes around. I cannot, as long as where I drag the node doesn't violate my diagramming rules, I'm good. The moment I try to violate any of the rules I've placed, I can't do it. You get this constraint interaction for free since you already told me how things should be arranged, right? So basically, you get an interactive diagram for free. So what's the vocabulary you can really use to express all of this? Spatial is deliberately really small, and it's divided into two parts. One family of rules describes how things should be laid out. You've already seen some of these, hiding, orientation, alignment, grouping. And the second family describes how things should be drawn. That's things like icons, colors, visibility. The visual zhuzh I mentioned earlier comes from these. No new spatial meaning, just makes things a little easier to read. And every rule operates over selectors, which are relational expressions that pick out which part of a graph the rule applies to. So that's the language. You might immediately wonder, how did we hit upon this design? You probably have several other questions people have about DSLs. Is it expressive enough? Is it fast? What do programs mean? What happens when they fail? The rest of the talk is going to answer all those questions. Let's start with where the operations come from. The design is grounded in principles from cognitive science, visualization, and diagramming. A lot of this work, if you're interested, across different fields and decades, keeps leaning on the same small set of ideas, and these ideas are basically where the operations come from. Which raises the question, is a vocabulary this small expressive enough for the diagrams programmers actually need? There's no benchmark for us to compare against here. I don't know how you'd want your value diagrammed in general, but there's a class of values for which we do have conventions. Data structures. We draw trees growing downwards, our stacks growing up, matrices as grids. So where can we find lots of data structures drawn the conventional way by somebody who's not me? You all familiar with this book? It's influential. It's an algorithms textbook known for its high coverage and carefully professionally drawn diagrams. If you learned algorithms through this book, you probably have some idea of how diagrams should be drawn, informed by this book. There are 22 core data structures in the book with corresponding diagrams. Spytial was able to recreate the essence of all 22 diagrams from corresponding Python implementations with very few refinements needed. The most was interval trees at 11 operations. So you can really just get these diagrams really quickly with often just five lines of code from the default. Okay, so it's expressive, but you also don't want to wait around forever to see a diagram. The REPL produces an output immediately, and that's why people like it. So does it run fast? Yes, graph goes up. Diagrams for most CLRS data structures render in under a second, well past the sizes of REPL output you normally inspect. Even at the high end, render times are roughly within standard interaction bounds. And I think the worst we got was 10 seconds for a really gnarly B tree. But all of this has been I've been talking about using the language. We're a PLDI. What does a program really mean? A spatial program is a set of constraints. And its denotation is the arrangements of the value graph that satisfy all of these constraints. The interaction video I showed you earlier is actually this denotation at work. You can drag elements around as long as the resulting arrangement is within the denotation. The empty program denotes every arrangement, which is how you get this diagram for free at the beginning. And then if you don't write any constraints, you just get the default graph. You got the empty program. And most importantly, and this is the crux of the paper, adding a constraint strictly refines the space of allowable arrangements. You can rearrange things, carve things out, but you can never invent stuff that isn't in the underlying value. The diagram you see is always faithful. And if the denotation of your program is empty, you know that it's unsatisfiable. It allows no arrangements, which raises the question, what happens when rules conflict? Let's add some constraints to our existing BDD diagram that say low edges go to the left and high edges go to the right. It may not be obvious looking at it right away, but it's not satisfiable for this BDD. So what's Spatial going to do? Like any well-principled tool, the first thing Spatial does is construct an error report roughly analogous to an unsat core. Basically a small set of diagramming rules that cannot be satisfied, and you can get that sort of error report in terms of the diagram elements or the general rules you wrote. But here's the problem with a purely textual report. The whole reason I want Spatial is because diagrams help me understand structure. The very moment I need a diagram most, a textual unsat core doesn't really help me out at all. So Spatial makes the error report diagrammatic. It draws a counterfactual diagram, what the value would look like if just the offending constraints were relaxed, and highlights the offending elements and links them back to what caused the conflict. Basically, the diagnostic itself is a diagram. And in our studies, these counterfactual diagrams, unsurprisingly, led to much faster comprehension than textual unsat cores alone. Hopefully, I've persuaded you that Spatial is worth trying out. Maybe you want diagrams. when you inspect values, and we should have this kind of inspection everywhere. So then I hear some of you thinking, does it work for my language? To study this, we integrated Spatial into 3 languages that occupy very, very different spaces on the programming languages spectrum. We have Python, which is super dynamic, runtime introspection, mutation, Rust, which everybody here loves, I think, statically typed, safety, and then Pyret, which is an educational language designed for teaching data structures with explicit ADTs. And, what we found is that if you hook into the same mechanisms the language uses to expose structure, basically what the REPL or the debugger would use, each language lends itself to the same rules and the same semantics. Which means if you want Spatial in your favorite language, the only thing you really have to do is hook into that mechanism. The diagrams, operations, error reports, interactivity, you get all of those for free. I mean, here's Spatial running in a Jupyter notebook, inline, totally for free. Basically, Spatial gives you a diagram when you need to inspect a program value. You start from a free graph representation of the value, refine it one constraint at a time, and stop when it meets your needs. You can play with our CLRS data structures here, learn about or install it in Python or Rust here. And I'm on the job market this year, so this is a really good time to argue with me about diagrams. Thanks so much. Yeah.
Thank you. We have 5 minutes for Q&A.
Thanks. This is very cool. So binary decision diagrams are often implemented with, instead of pointers for low and high, integer IDs into like a node table.
Yes.
Does Spatial have some way of handling that kind of indirection?
Absolutely. You can, let me go to a slide of the, yeah. So one thing you can do in Spatial is while you can't invent nodes, you can invent what I call inferred edges. These are kind of like when you're doing a program, when you're doing a proof, sometimes you have these like ghost fields you input. You can basically say draw an edge that matches this relational selector, and so you can do that to kind of simulate edges from an implementation. It's like kind of similar when your backend is an array, but you want to see a heap kind of thing.
So this is Rachel from MIT. Great talk, beautiful work. I wanted to go back to the question about larger diagrams. Mm-hmm. One thing that I really want to do if I'm looking at BDDs is generate really big ones and be surprised about why ordering of certain variables is causing issues in my particular domain, right? And so in that case, we really do care about really big diagrams where we don't know which section we want to focus on, and we're looking for surprise. I'm curious what mechanism and sort of how you think about this problem and how you can help me solve it.
Yeah, so I think about this in 2 ways. Number one, generally I think of like, when I look at anything in like in the REPL, beyond 50 nodes, I'm like, all right, I'm not able to like it's already like scroll down to the next page, right? So in general, that's why I kind of thought about this up to 50. That said, like, there's nothing preventing Spatial from rendering things that are larger. It just might take a little longer. It's also just the first layout. Once the solver is solved, you're good. Yeah, for that.
Thanks.
Yeah.
Hi, this is Justin from UC Berkeley. Thank you so much for the lovely talk. Really enjoyed it. I really appreciate that you think about what happens when the constraints are unsatisfiable, and I liked your analogy to the unsat core. But something that struck me as interesting is that you have this sort of like linear process of creating the program of like you're refining the graph one by one, whereas in something like sat, all the constraints are kind of there, and then you like run it, and you don't know like what to do. So I'm wondering if you can like exploit the way that like people are actually like writing these refinements to get maybe even better sort of error handling.
Yeah. So in one sense, Spatial is fully order independent because of this sort of set-based semantics of constraints. So you could give it everything just like you give a SAT solver, and it would produce exactly the same behavior. I think the really neat idea is that what I think people can exploit is you write all your rules and now you can toggle them on and off, and because of these refinement semantics, it never behaves weirdly, so you can kind of really isolate where it came from. Does that, yeah, thanks.
Yeah, thanks for the talk. Seems like a very cool tool. One thing that I sometimes want to do is to be able to view the state of some system across multiple time steps, so across multiple diagrams. And ideally, I don't want the nodes to be jiggling around from one diagram to the next. Is that something that you support or that you could add?
This is a great question. So something I'm looking into right now, Spatial, each diagram is independently laid out. So this is like some union find algorithm, and basically when you add some parent to satisfy the rules, Spatial does a full reload and everything there goes there, basically. I have some thoughts about using soft constraints to kind of keep things in place. And newer versions of the system have some mechanisms for this. But yeah, so I'd love to chat with you more about that. Yeah. Yeah, awesome.
Thank you for your talk. One thing I did not get is, do you only take the REPL output and construct it, or can you monitor a runtime data structure?
Oh yeah, so the REPL is just an analogy I'm using. It's any way you would like any way your language exposes structure. Like Rust doesn't have a REPL, but it has a serializer, and people use that to kind of keep track of what's going on. It's all of these different languages have different ways of exposing structure, so as long as you can tap into that, and most languages provide hooks.
Do you think this can be extended to simulate algorithms on the structures?
So I think that's the same, a little bit of the same question, right? Like with algorithm visualization, you can naively. I think the main thing is what's very useful is often having these sort of softer constraints of keeping nodes in the same general area if you can help it to prevent this kind of jitter. Yeah.
Okay, thanks.
But yes, long story short.
Hi. I think this is a very timely needed software. My question is, I work with a lot of sparse tensors. How would you represent them in this in a graphical structure?
Yeah. It depends on how the language represents them. So often
like Python sparse tensors, PyTorch, for example.
So I couldn't tell you specifically about sparse tensors in Python, but maybe this is an example of, it's really nice that Spatial doesn't add values to the graph, but you get the actual underlying structure that the language exposes.
So my next question is that this example would work if the tensor is small.
Yes.
But the tensors that are usually used in practice are huge. And so I was wondering the scalability with the number of nodes.
Well, I guess my question is, would you ever print out the huge tensor?
Yeah, for example, if I want to see is there a structure in the sparsity, so I would print it out, for example, one row per line. So I would use the whole screen, but I'm not sure how would you represent in a graphical way like this.
So Spatial can run across all of these different sizes. The question is, you need to be able to write the rules then to refine it to the structure that works for you. But I think the general analogy is anything that's at the size of the REPL is kind of the size you can, or debugger is the size you look at things.
Okay, let's thank our speaker again.